What if artificial intelligence could understand the laws of physics, not just mimic data, but obey the same equations that govern the universe? Imagine neural networks that not only predict outcomes, but respect the conservation of energy, momentum, and mass, just like nature does. Welcome to the world of physics-informed neural networks, or PINs, the bridge between physics and artificial intelligence, and one of the most transformative ideas shaping the future of scientific computing. You're watching The Learning Studio, and in today's episode from our physics playlist, we'll explore how scientists are teaching machines to think like physicists. You can check out the entire physics playlist by clicking the link in the video description below. This topic belongs to our section, Physics Meets AI, the Computational Frontier, where the logic of the universe meets the learning power of neural networks. The problem: why AI needs physics. AI has changed everything, from voice assistants to image recognition. But in science, it faces a big problem. It doesn't know the laws of nature. Traditional neural networks are data hungry. They learn from examples, millions of them. But if the data is noisy, incomplete, or inconsistent with real-world physics, the results can go wrong. For instance, a neural network trained to predict airflow over an airplane wing might give a result that looks fine, but violates conservation of mass or momentum. In physics, that's unacceptable. So researchers asked a powerful question: what if we could build neural networks that know physics? That question gave birth to PINs, neural networks guided not just by data, but by the laws of physics themselves. The idea: teaching AI the laws of nature. A physics-informed neural network works like a standard AI model. It takes inputs, processes them through hidden layers, and produces predictions. But here's the twist. Instead of training the network to simply minimize data errors, we also train it to satisfy physical equations. For example, if you're modeling a vibrating string, a fluid flow, or heat conduction, those systems follow differential equations, like the Navier-Stokes or Schrödinger equations. PINs embed these equations directly into their learning process. This means the AI doesn't just fit the data, it must also obey the physics that generated that data. In simple terms, a traditional neural network learns what happens. A physics-informed neural network learns why it happens. How PINs work, the core concept. Let's break it down. Define the physical system, say, fluid flow governed by the Navier-Stokes equations. Set up a neural network that takes coordinates like position and time as input. Compute derivatives of the network's output with respect to these inputs using automatic differentiation. Plug those derivatives into the physical equations. Train the network so that the equations hold true, minimizing both data error and physical error. The result? An AI model that not only fits observations, but inherently respects conservation laws, symmetry, and boundary conditions. This makes PINs incredibly data efficient. They can learn from just a handful of examples because the physics itself guides the learning. Applications: where physics and AI unite. The power of PINs is already reshaping scientific research and engineering. In aerospace, they simulate fluid flows around aircraft faster than traditional CFD models. In biomedicine, they model blood flow in arteries and heat transfer in human tissues. In fusion energy, they predict plasma behavior, crucial for maintaining stability in reactors. In geophysics, they're used to model seismic wave propagation deep underground. And in materials science, they simulate how heat, stress, and quantum effects interact at atomic scales. But it doesn't stop there. PINs are becoming the foundation of what's called scientific machine learning. AI systems that don't just process data, but truly understand the physics of reality. Why PINs are revolutionary? The key difference is interpretability. Most AI models are black boxes. They tell us what happens, but not why. PINs, on the other hand, are transparent and trustworthy because their structure is rooted in physics. They respect physical constraints, making them ideal for safety-critical fields, like climate modeling, nuclear engineering, or medical simulations, where a small error could mean a huge consequence. And because they use the laws of physics as their guide, they can extrapolate far beyond the data they've seen, something classical AI often fails to do. The future: intelligent simulations of reality. In the next decade, physics-informed neural networks will become the core of digital experimentation. They'll power AI-driven laboratories, real-time climate simulators, and autonomous scientific discovery systems capable of running millions of experiments virtually. Imagine AI scientists that can run quantum or relativistic simulations, checking each step against the known laws of physics while discovering new ones along the way. Combine this with quantum computing and digital twins, and we'll have a future where every physical process, from weather systems to galaxy formation, can be simulated with stunning accuracy, efficiency, and insight. Why this matters? Physics-informed neural networks are more than a new algorithm. They represent a new philosophy of learning. They show that intelligence doesn't come from data alone. It comes from understanding the rules that shape the data. By merging physics with machine learning, we're teaching AI not just to think, but to reason about the universe itself. For students, this means entering a field where knowledge, computation, and creativity unite. For researchers, it means accelerating discovery. And for all of us, it means unlocking a future where machines don't just model nature, they cooperate with it. This is the Learning Studio, and this was our episode on physics-informed neural networks, teaching AI the laws of physics. If you enjoyed exploring how intelligence meets the universe's most fundamental principles, make sure to like, subscribe, and check out our physics playlist linked below. In our next episode, we'll explore AI-augmented scientific discovery, where neural networks don't just simulate physics, but help uncover new laws of nature. Because the next revolution in science won't come from more data. It will come from AI that understands the physics behind it.